Welcome to lecture 37 on risk management and insurance. In this and the next few lectures, we cover Copulas. The main source for those lectures is McNeil, Frey, Embrecht's Quantitative Risk Management. And the prerequisite, the mathematical prerequisite for this book is that you have a second year class in university statistics. Only with the first year level, you probably it will be difficult for you to read this book. So you should have a second year university level course in statistics to appreciate this book. Now, let's, in the current lecture, we just review a bit of statistics. And then in the next lecture, we go to the Copulas. So first, the concept of the cumulative distribution function. In equation 1 here, a cumulative distribution function shows the probability that a random variable x takes the value that is equal or less than the critical value small x. That's a function value of the cumulative distribution function. So be careful here. It's a common notation. So for the random variable, we use a capital X. And for the critical value of the random variable, for some critical value or some specific value of the random variable, we use a lowercase letter. So here it's a probability that this random variable takes a value of less or equal this critical value here. This probability is actually shown by the cumulative distribution function. And so here in the cumulative distribution function, you should have a small x. It's a common error that sometimes you see that people are using here the capital X, but it's a small x. It's about this here. The random variable takes a value of x or less of this critical value or less. Okay, so you should write here the small x. Now the domain of the function can be between minus infinity, plus infinity, or from 0 to infinity, or between 0 and 1. So the domain, but there are also other domains. And the range goes from 0 to 1 naturally because the range of the function or image of the function, it shows a probability. And the probability is naturally a value between 0. It's a number between 0 and 1. You probably know the notation. A cornered bracket means that the border is also included, that it's a closed interval. So here, the number 1 will also be included. With both bracket, it's an open interval. That does not include the border. Now, the definition of the probability density function, the PDF, it's a piecewise function, small f, such that the function value gives you the CDF, the cumulative distribution function. So here I have the PDF, the probability density function, and if you integrate this probability density function from minus infinity to up to some critical value x, then you get actually this probability, okay, that is shown by the cumulative probability distribution function. So the PDF indicates the rate of change of the CDF. We can, let's use the fundamental theorem of calculus. So the fundamental theorem of calculus shows you how to take the derivative of an integral with regard to the limit here. And what you get is actually just a function value at the limit, f of x. Now that's naturally very central in calculus, and if you have a first-year calculus class, you will know about the fundamental theorem of calculus. How do you take the derivative of this integral with regard here to the upper limit? It's really actually just the function value at the upper limit, fx. So that gives you the PDF. Now let's these graphs, those graphs here are shown typically in introductory statistics classes. So we have here down here the PDF. Okay, the probability density function. And then up here I have the cumulative distribution function. And so if you integrate here up to this critical value x here, then you get the probability, that the random variable x has a value of less than this critical value here. And that's actually shown up here. The CDF shows you that probability. So here on this axis, it goes from 0 to 1. So here I have the probabilities. So you integrate the PDF up to some critical value x, and then you see here the blue arrow, that's a probability that the random variable takes a value of less than this critical value, less or equal to this critical value. The probability is here in this example 0.95. So if you go from the PDF to the CDF, you integrate. If you go from PDF up to the CDF, you integrate. So that's what we have done here in equation 2. You see, you integrate from -infinity up to the critical value small x under here under the probability density function. And this gives you the value of the CDF, of the cumulative distribution function. So you integrate up to here x, and then this blue arrow here gives you the value of the cumulative distribution function. The cumulative distribution function we said shows you the probability that the random variable x has a value of less than this critical value small x. That's where we started. The cumulative distribution function is the probability that the random variable x has a value of less than or equal some critical value small x. So if you think in terms of equation 2, you go from down here to up here. If you think in terms of equation 3, then you go from up here down here. You differentiate, and you get the rate of change. So you differentiate the cumulative distribution function, and then you get CFX. That's the rate of change. Differentiating the cumulative distribution function gives you the rate of change of this CDF, and that's just the f at the point x. So the rate of change here of the cumulative distribution function here, is shown down here. And always is a rate of change gets bigger and bigger and bigger here, and here it has a maximum. So the rate of change gets bigger, bigger, bigger. Here it has a maximum, and then the rate of change again starts to fall. Okay, so here it again starts to fall. So if you think in terms of equation 3, you just simply differentiate and you calculate the rate of change. You calculate the rate of change, and to differentiate here this CDF, you have to differentiate with regard to the upper limit here, okay? So you need the fundamental theorem of calculus. Okay, so that's all material out of a first year calculus class at university level. Now, let's suppose the CDF is continuous, the cumulative distribution function is continuous and strictly increases, in that case it has an inverse. So we have here the CDF, and let's assume it is strictly increasing and continuous, then it will have an inverse. Okay, so fx, you take the inverse, you're back to x. For all, this means for all, okay, x is in the domain of the function. Now you will be in trouble if your CDF has a flat portion. In that case, it will not have an inverse. But you can work with a so-called generalized inverse, and you can look this up in McNeil. I'm disregarding that. Let's just repeat this again on the inverses. Okay, so let's have here the function. It's always upward sloping, strictly increasing and continuous. Now such a function will have an inverse and it will look somehow like this. Now if the function is declining somewhere, I make it easy here, it's difficult to draw pictures. So let's assume it declines here just at the end. Yeah, that one I have to remove again. So let's just move it declining here at the end. Such a function has no inverse. The inverse would look somehow like this. You see, it would bend backwards. But that's not the function because it's not unique. You see the x value here actually have two values. And the function must be unique. It's only allowed to have one value. So a function that is declining, not just here at the end, at high values, just that is declining anywhere, okay, will have no inverse. And the flat portion is actually even the inverse. Let's assume the function has a flat portion. Again, I make it simple. I do the flat portion here at the end. Now the inverse would look somehow like that. Okay, with a vertical portion. As it should be vertical here. And that's naturally also not allowed. Okay, that is not a function. Okay, it's a function must be unique. Now, conceivably, you will have flat portions. You can have flat portions in cumulative distribution functions. So maybe here suddenly here, it's no longer increasing, and then later it increases again. So that would be possible. So you have a flat portion. In that case, down here, just the frequency would be 0 over the range of the flat. So the frequency here would be 0. So that's naturally possible. Now, what you cannot have is a declining CDF, because then, okay, the frequency would be negative. Then you have here a negative probabilities, and that's naturally nonsense. So flat portions are possible, and but you can deal with them. You can look up in McNeil, Frey, Embrechts, okay, how they deal with the flat portions, and then you're a bit more general than what I'm doing here in this course. I neglect the flat portions. I just simply assume there is an inverse. Now the inverse is called the quantile function. It's also called the quantile function. And the alpha quantile of a random variable x capital letter, random variable x is the value x alpha, so that the probability that the random variable x is less or equal x alpha is just equal alpha. So let's do that here. So I have here a critical value 1.64 in this a normal distribution. Here that only naturally applies for the normal distribution. I have 1.64, and the probability that the random variable will be less or equal 1.64 is 0.95. Okay, that's 0.95. So I have here actually a 0.95 quantile. 1.64 is a 0.95 quantile. You see, it's 0.95 here. The probability that x is less than 1.64, okay, is just 0.95. So I have here the 0.95 quantile. The inverse, here I show the inverse for the normal distribution. You begin here with the inverse, you begin with the function value of the CDF. So down here it goes from 0 to 1. Down here has the probabilities. And then you go back toward, okay, the x values. So with the inverse, you start up here with the probabilities, perhaps 9.5, and then the corresponding x value is 164. That's naturally, okay, easy stuff, okay, from introductory statistics courses. So with the inverse, you start at the 9.5, okay, and you go back to the 164. In econometrics classes, the inverse CDF is also sometimes called the probit function. Let's make another example, the standard uniform distribution. Let's assume we have a random variable u. I call it now here u because okay, it has a uniform distribution, so I use another letter. It's important that I take here a capital letter, okay, because the random variable, that stands for the random variable. And if it's a standard uniform distribution, then it's actually defined on the interval 0 to 1. That's the domain of the function, this closed interval here. So let's assume u has this uniform distribution on the interval 0, 1. Be careful here, that actually gives me the interval of the domain of the function. So that's not the mean of 0 and the standard deviation of 1. Now, if you think of the notations that you use for the normal distribution, then this will be the mean and this will be the standard deviation. But here, with a uniform distribution, the 0 is actually just okay, the lower limit of the domain, and the 1 is the upper limit okay, of the domain of the function, or of the interval over which the function is defined. Now the CDF for the uniform distribution is very simple, and then the PDF, okay, is just a constant. Let's look at that. So you probably know the uniform distribution. We have here a CDF, which is a 45-degree line. And we have a PDF, then actually which is just a constant equal to 1. You see, we said if you go from top to below, you take the differential. You differentiate. Now here, the rate of change is naturally 1. So you have here the 1. It's a 45-degree line. And if you go from below to the top, then you integrate. And actually, if you integrate here beneath this constant, you just get the 45-degree line. So that's the uniform distribution. Also here, maybe note 1 times 1 gives us naturally just a probability of 1. Okay, the interval here is 1, and so naturally here the density must be 1, the constant density, because the error, okay, must be 1. Okay, something has to happen. And then also the inverse is again just u. You see, if you have a 45-degree line, you take the inverse now of this function, then again you get the 45-degree line. So that's a uniform distribution. We will use it very often, this uniform distribution. So each small interval here, okay, has the same probability. So constant. Now let's look at the bivariate probability distribution. So here we just extend it now to two random variables, and the cumulative distribution function is a probability that the random variable x is less than the critical value small x, and the random variable y is less than the critical value small y. So again, here you have the small x and the small y. Those are the two critical values. And those are the critical values that you have up here in the integral as the upper limits. So you have now to integrate the probability density function. You have to integrate it first up for the y variable and then for the x variable. You go up to the value y and you go up to the value x. You do both integrations. Now here, I do not write x and y again because it would be confusing. You see, he has a lot of x and y's. So it's actually common then to rename the variables u and v. But the first one actually stands for the integration along the x-axis, and the second one stands for the integration along the y-axis. And then you can apply the fundamental theorem of multivariate calculus. You just do this cross derivative, this partial cross derivative, and you get then the joint PDF. So you make the derivative with regard to x and the derivative with regard to y, with regard to the upper limit, and then you get the rate of change here. Okay, which is a joint PDF. Now, what's very important then in the next chapters that we do on the copula is the marginal CDF. The marginal CDF shows the probability distribution of x, whatever the value of y. So it's a probability that x is smaller than this critical value, whatever the value of y. So y does not appear here. So so you integrate up to the small x, and the y can be whatever between minus infinity and plus infinity. So that gives us the probability distribution of x, whatever the value of y. We indicate this marginal CDF here with a subscript x. And here for the subscript, I use actually the capital letter X because I mean here it's a marginal distribution of the random variable X. And it shows us the probability of this random variable taking a value up to or equal this critical value, whatever the values of the other as a random variable. And you can naturally also do this for y. Now again, you can differentiate this with regard to small x. So let's get the rate of change of this marginal CDF. Then we get the marginal PDF. This again requires the fundamental theorem of calculus. So make the derivative of this with regard to x. What you get is just a function value here at the point x and y. So y we already have it, and so u becomes the x. Okay, that's maybe useful to repeat. So we make sure that we use some fundamental theorem of calculus, and we get now just a function value at point x and y. So the marginal frequency of or the marginal probability density of x you get by integration over y. So integration goes here over y. And those concepts can be extended naturally into 3, 4, 5 and more random variables. So you can also deal with higher dimension probability distribution functions that have more than 2 random variables. Now here I show you the marginal PDF. So I have here a bivariate distribution x and y. And so the marginal distribution of x is here. It shows you the probability density of x, whatever the random variable y. So you actually do the summation over the y. You see here we have only one observation, so that's the frequency is very low here. But then here we have a lot of y's, so the frequency is high. So you must integrate over the y. Integrate over the y to get the marginal distribution of x. That's what we said here. Integrate over the y to get the marginal distribution, the marginal PDF of x. You integrate over y. Okay, you have to think a bit about that one. Now here, that shows in the other way, if you want to have the marginal distribution of y, then you have to integrate over x. So you see here we have a lot of x's along this line, so that's a high frequency here. Here we have only a few x's, so that's a low frequency. So you will integrate over the x to get the marginal distribution of the y. Now this here is the marginal PDF. And those graphs you now see quite often, and you can do it very nicely actually with R. I did this one with R software. What you also would like to have is the marginal CDF. The marginal CDF would look somehow like this. And also here. It would look somehow like this. That's the marginal CDF. So you see here, I started with the marginal CDF. So marginal CDF shows the probability distribution of x, whatever the value of y. Okay, so what is the probability x smaller than some critical value, okay, whatever the value of y. That would be, actually here's this red line. What is the probability of here of x, whatever the value of the random variable y? I have not found a way actually in R to plot this marginal CDF, okay, this red line. There are very nice graphs, okay, with the PDF, but the CDF, okay, that's something you have to program yourself if you really want to do it. I have seen no programs. Okay, so that's those marginal distributions will become very important in the next lecture. Okay, so that was the lecture for today. Just a repetition a bit of statistics, and we will now then go to the copula in the next lecture. Thank you.